Hi again, everyone. This is going to be another lesson on trig identities. In the past two videos, we've been referring to a reference sheet that I posted of some trig identities, and it looks something like this. So make sure that you have a copy of this. You know it's posted where I usually post worksheets, and make sure you have that for this lesson printed out because we're going to refer to it a lot. Okay, so there's still some trig identities on this sheet that we haven't gotten to yet, and that's what this video is going to be about. I think if you look at the sheet, we've already talked about the fundamental identities, and then if you skip ahead a little bit, we've talked about the addition and subtraction formulas. That was the last video. Now, the cofunction identities and the reduction identities, those can be proved in a couple of different ways. But I think that maybe the most straightforward way to prove them is using the addition and subtraction formulas. So, because all of those are an addition or a subtraction with a trig function. So that takes care of about half of the sheet. And then we said that the law of sines and law of cosines in the lower right, they kind of don't count. They're not really trig identities. They're triangle identities that we learned in a previous chapter. So what does that leave that we haven't talked about yet? I see double angle formulas, formulas for reducing powers, half angle formulas, product to sum, and sum to product identities. All of that is going to get covered in this video. So let's go ahead and get started. All right, so this section has a long title. It's something like double angle, half angle, and product sum formulas, but I'm just calling it more trig identities. So let's just jump in and start talking about the first type, which is the double angle formulas. And kind of like we did in the previous video, we're not going to derive every single one of these, because I guess under the double angle formulas, there are kind of 5 different identities. I mean, I see sine 2x equals something, tangent 2x equals something, and then I see cosine 2x equals 3 different formulas. So altogether, there's 5 formulas. We don't necessarily need to prove everything in this class. So first of all, we said in the previous video, the addition formula for cosine looks like this. Right, and that's on the reference sheet also. That's not a double angle formula. I'm just beginning the discussion of double angle formulas, and I'm starting by recalling an addition formula. Okay? This is the addition formula for cosine. So what happens if we try to do cosine of x plus x? What if the two angles that are being added are in fact the same angle? Instead of x plus y, we just say y is the same angle as x. Well, in that case, you get cosine x minus sine x, sine x. And we rewrite this as, what's the left-hand side? The left-hand side could be written much more simply as cosine of 2x, because that's what x plus x is, 2 copies of x. The right-hand side could be written more simply as cosine squared x minus sine squared x. I'm going to put a box around this, and this is one of the double angle formulas. See how quickly we derived that? We derived it very simply because it just comes from one of the addition formulas. I also want to point out that you might be looking at this and saying, wait, there's a sine squared and there's a cosine squared. Don't we have a fundamental identity involving those two? Well, if this were a plus sign, sine squared plus cosine squared equals something, right? So I'm going to say since sine squared x plus cosine squared x equals 1, then there's a couple of things we can do with it. We could rearrange to say sine squared x is 1 minus cosine squared x. And we can also say cosine squared x equals 1 minus sine squared x. Right now I took the fundamental identity, solved for sine squared, or solved it for cosine squared, just by subtracting something from both sides. So we could put that into this double angle formula. And that's why there are 3 different versions of the double angle formula for cosine. You take the one that we put a box around and merge it with either of these 2 statements. So what happens if we take the first statement? Say, we're going to replace sine squared x with 1 minus cosine squared x. What would that look like? Would that help? So we'd be doing cosine squared x minus 1 minus, what's going on here? We'll write it out. Let's write it out and see what happens. All right. Like that. I was trying to say it out loud, but it was confusing because I wasn't saying the parentheses. So let's just write it. Because of these parentheses, we have minus cosine squared. So that means we're adding it. So we have the cosine squared plus cosine squared. So we get 2 cosine squared x minus 1. I'll put the left-hand side again. This is another one of those double angle formulas on the reference sheet for cosine. It's called a double angle formula because on the left we have twice an angle. X is an angle, twice an angle. You do cosine of twice an angle and you get this. Or this. They're both equivalent. Also, we can use the other one. So instead of swapping in 1 minus cosine squared for sine squared, you could do the other thing. Swap this in for cosine squared, and I'll just write that one. That's the one where you wind up getting 1 minus 2 sine squared x. So that's why on the sheet, 3 different things here for cosine 2x equals this, equals this, equals this. That's what we just did. Equals this, this, this. So those are called double angle formulas for cosine. And what about the other ones? What about sine? What about tangent? So what I'm going to do is I'm just going to say that if we understand this argument here, we could do the one for sine a little bit quicker. So I'll just tell you that if you used sine 2x equals sine of x plus x, and you used the addition formula, just like we did above, but this time you're using the addition formula for sine. And for tangent 2x, if you used the addition formula for tangent. That is how you would find that sine 2x equals 2 sine x cosine x. And that's how you'd find that tangent 2x equals this. So these double angle formulas, all of them have sine, cosine, or tangent of 2 times an angle. And the right-hand sides, notice that the right-hand sides involve x, but they don't have 2x. They don't have any 2x's. So it's like the original angle appears on the right-hand side, but 2 times the angle appears on the left-hand side. We'll see an example of a problem that uses that in a little bit, but I want to cover some more identities first. So we just derived these. We can check those off the list of trig identities we've derived. And now let's talk quickly about formulas for lowering powers or reducing powers. So, at the beginning of this video, I said that on our reference sheet, I think there were 4 different categories of trig identities that we hadn't gotten to yet. Formulas for reducing powers was one of them. But then, what's the title of this section? Double angle, half angle, product sum. Oh, so the formulas for reducing powers didn't even make it into the title. All right, well, we're going to talk about them anyway. They didn't make it into the title. Maybe they're considered less important. I don't know. So let's take something that we wrote above. We wrote that above. That's not a formula for reducing powers. I want to be clear. This is just us starting from something. What I put a box around is going to be a formula for reducing powers. What if I take this and solve for sine squared x? Sine squared x equals. What rearranging would we have to do to get sine squared equals? Sine squared x equals. Well, we'd subtract 1 from both sides, and then we divide both sides by -2. You wind up with this. So you see, this is under the list of formulas for reducing powers, but it's really just a rearranged version of one of the double angle formulas that we wrote above. There's the double angle formula. We rearrange it, and we give it a new name. So I think that's why this type of formula didn't make it into the title of this section. It's because they kind of follow from just a single step. It's just a single rearranging step, and you get a rearranged version of the identity. What if I started with cosine 2x equals 2 cosine squared x minus 1? That was another thing that we wrote above today. And what if I use this to solve for cosine squared? That's a good idea. We solved for sine squared in the other one. You wind up with 1 plus cosine 2x over 2. And that is also considered a formula for reducing powers. All right, now, tangent is probably more complicated, right? Tangent is usually just a little bit trickier than sine and cosine. So here's what we're going to do. We want a formula for reducing powers for tangent. So I want tangent squared x equals something. What I'm going to do is I'm going to use the fundamental identity, that tangent is sine over cosine. So if tangent squared is sine squared over cosine squared. And up top, I'm going to replace sine squared x with this thing we just found. And on the bottom, I'm going to replace cosine squared x with this thing we just found. So it's kind of like putting one identity over another. And then we'll see if it simplifies. Put a big division bar there. I mean, technically, this is a trig identity, but it's something that we could write simpler. So we put one identity over another. So the simplified version of this is to say, we don't like having a fraction inside a fraction. A nice, simple way to deal with this is multiply this whole thing by 2 over 2. If you multiply the whole thing by 2 over 2, you get 1 minus cosine 2x up top, 1 plus cosine 2x on the bottom. So that's the formula for reducing powers for tangent. Now, before we move on, I want to talk about, why are these called formulas for reducing powers? Can you see why they're called that? It's because on the left-hand side, you have a trig function with a power of 2. And on the right-hand side, you have a trig function with a power of 1. That's why it's called that. You're going from a power of 2 trig function to a power of 1 trig function. Now, it might not even go to the same trig function. Sine squared x turns into this form of cosine. So it's like taking a second power trig function and turning it into a first power trig function, but it might not even be the same trig function you started with. In a way, it's sometimes helpful, though. In general, I think in math, anytime you can reduce powers, like, if you had a large exponent and you can somehow turn it into a smaller exponent, that can sometimes be helpful. It can sometimes be considered simpler. Depends on what you're using it for. So, let me show you an example problem. We're going to kind of alternate. In this section, we're going to go back and forth between deriving identities and using them for problems. So here's a problem. It's going to be a little different from some things you've seen. Express sine squared x, cosine squared x in terms of the first power of cosine. I'll do this one for us. All right, let's move away those old trig identities. I think we've got them all now. All right, so what can we do here? We want to, well, we have something that's given to us in a second power of trig functions, and we would like to write it in the first power of a trig function. So yeah, this is where the formulas for reducing powers come in. We could say that sine squared x cosine squared x is equal to this thing times this thing. But we should see if we could simplify this or write this in some nicer way. I mean, that's kind of implied, express it, blah, 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 and simplify your answer, right? Isn't that kind of implied, simplify your answer? All right, so what if we multiply these out? I'm kind of afraid that if I multiply these out, it's going to become cosine squared, isn't it? If it becomes cosine squared, then we haven't really answered the question. Let's expand it out and see what happens. Distribute. Yeah, we get cosine squared. On the bottom, 2 times 2 is 4. So we haven't really answered the question because we expressed it in terms of, we could cancel these, but we've expressed it in terms of the second power of cosine. That doesn't help. Here, let's get rid of the stuff we canceled and just write it this way. So we're not done yet. We're not done yet. All right, there's a couple of different ways we could probably go from here. This 1/4 is bothering me, like the 1/4 is bothering me, so I'm going to split it up and say this is 1/4 minus 1/4 cosine squared 2x. I'm just trying to get the cosine squared 2x by itself. I don't know if you want to do that step or not, but I'm looking for a way to get this to be just in terms of the first power of cosine. Right now it's the second power. So here's an idea. What if we use the formula for reducing powers again? Okay, so we used it on this piece. Here, I'll underline some things. We used a formula for reducing powers on this. We used a formula for reducing powers on this. Now I'm going to use the formula for reducing powers on this. So 1/4 minus 1/4. Let's put parentheses here and figure out what needs to go in here. The angle that we're putting in is not x this time. This time, the angle that we're putting in is 2x. So we can still use the identity. Let me just point out to you which identity we're using. I want to use this. All right, so I want to use this thing I'm pointing at with my pen. and I want to use it on this guy right here. Cosine squared of x was supposed to equal this. So what is cosine squared of 2x going to equal? Well, the answer is we can use the same identity, but instead of x, we have 2x. So this is going to be a 2 times 2x. 2 times 2x is going to be 4x in this spot. So I'm going to write that. I'm going to say that this is 1 plus cosine 4x over 2. All right, understand that? So I'm saying it's okay to use this identity. X is kind of replaced with 2x, so this x has to get replaced with 2x. There's already a 2 in front, so when I replace this x with 2x, it's going to be 2 times 2x. That's where this 4 came from. And look at that. We expressed it in terms of the first power of cosine. So I think one more thing that I'll do, because now we've got a fraction, mine's a fraction, there's a 2 down here. What if we combine like the 4 and the 2? That would be nice. So I did a couple more simplifying steps. I said this is 1/4 minus 1/8 minus 1/8 cosine 4x, which is 1/8 minus 1/8 cosine 4x. So that is equivalent to the original problem, but now it's only in the first power of cosine. Or I guess another way you could write it is if you wanted to pull out the 1/8, you could do this. Either one of these looks good to me. There's another method for solving this, by the way. I think I'll show you the other method also. And just to be clear, because we're going to do a bunch of examples today, this is an example of formulas for lowering powers. It's one type of problem that you could see that uses that type of trig identity, because I'm going to try to show you that all these trig identities can be used for something. All right, so what we did, I'm going to relabel it as solution method 1, and I'm going to show you a solution method 2, and then you can decide which one you like better. They're going to lead us to the same answer. I guess in method 1, we applied the reducing powers formula twice. So let's pretend we haven't done any of this work yet and show you another method. So we have sine squared x cosine squared x, and we want to apply something to it. So another way that you could view this problem is you could say this is sine x cosine x, all of that squared. And then try to think of something that you can do with this. And you might have to look through your reference sheet and say, you know, all right, I'm checking the ones we know, looking maybe the fundamental ones. Do you see anything that has a sine x cosine x that might be useful? I do see something that has a sine x cosine x. And it's right here. It has a 2 in front also, but it has a sine x cosine x, and it's kind of the only thing in this sheet that I see that has that. So let me write some of this off to the side. All right, so we noticed the identity, this thing here. And I'm wondering, is there some way that, you know, because this has sine x cosine x and this has it also, we could rearrange this to say sine x cosine x is equal to sine 2x over 2. So that means that this is equal to sine 2x over 2. The whole thing is still squared. Here's what I'm going to do. When we square a fraction, we have to square the top and the bottom. So let's write this as sine squared 2x over 4. The 4 could actually be pulled out front as 1/4 if you want. What is sine squared 2x? Remember what we're trying to do. It says express this in terms of the first power of cosine. So now I'm going to use the formula for reducing powers, the formula for lowering powers, because sine squared 2x, up here we did that on cosine squared 2x. And remember a 4x appeared? We do the same kind of thing here. A 4x appears. And in the end, I wind up with 1/8 1 minus cosine 4x. Remember, we're solving the same problem that we did above, so we should get the same answer. Did we get the same answer? Yeah, we did. So, which method do you think is easier? I guess in method 1, I had to use the formula for reducing powers twice. And there was some other stuff too, right? Like we had to do this algebra. We had to expand, find things that cancel. Maybe there was a little more dealing with fractions. 1/4 minus 1/8 is 1/8. The second method, it seems like we wrote fewer steps. But the trick was we had to notice, first of all, you had to notice that you could go from this first step to the second step. And then you had to notice that the sine x cosine x could be written in this way. And that's something that might not be so easy to notice. But by putting that in, maybe you could say it feels like it saved us a step. But anyway, that's just to show you that in some of these trig identity problems, there could be more than one way to get to the correct answer. As long as you're showing your steps and justifying your answer, that's what matters. So we have another class of trig identities that are important for us to talk about, and they are the half-angle formulas. And I'll tell you how we're going to derive them, and it's a 3-step process. And you start with the formulas for lowering powers, which we already know why these are true. We replace x with u over 2. Now, are we allowed to just take an identity and replace a variable with something else? Well, the answer is yes, because identities are true for all values in the domain. So whatever angle x is, you could just define u so that x is equal to u over 2. And then step 3, we take the square root of both sides. So I'm explaining how we derive the half-angle formulas, starting from the formulas for reducing powers. And I guess there were 3 formulas for reducing powers, so there are going to be 3 half-angle formulas. So the result of doing this 3-step thing, you get sine of u over 2 equals plus or minus. When you do the square root of both sides, there's a plus or a minus that shows up. So you get this, would be called a half-angle formula for sine. You get this, which would be considered a half-angle formula for cosine. They look very similar. what's the deal with the plus and minus, though? Like, is it plus or is it minus? And I'm going to tell you the choice of plus or minus depends on which quadrant u over 2 is in. We're doing sine of u over 2, or we're doing cosine of u over 2. So u over 2 is the angle that we're interested in. It's pointing towards some quadrant, and in whatever quadrant u over 2 is pointing to, we can figure out if sine is positive or negative in that quadrant, if cosine is positive or negative in that quadrant. For example, if u over 2 is an angle that's small enough that we're pointing into quadrant 1, for example, if it's quadrant 1, then we know sine is positive and cosine is positive. So you don't actually have a plus or minus symbol in your answer. You determine, is it plus or is it minus, and then you write the correct one. What about tangent? What about tangent? I'll show you tangent. How do we get the one for tangent? I guess we could do the same thing, and if we do the same thing, we wind up getting this. Like, if I do the three-step process, it gets me this. But you might look at this and say, well, that doesn't really look like the half-angle formula on the reference sheet. So why does this look different from the formula on the reference sheet? It's because further rearranging has been done. And I'll show you what further rearranging we wind up doing. It's actually kind of interesting. All right, plus or minus. We're going to multiply this by something, this fraction. Under the square root, we're going to multiply by something that's going to help us rearrange it. This is something that you usually wouldn't think to do, but, you know, sometimes proofs in math use clever little tricks like this. We're going to multiply by 1 minus cosine u over 1 minus cosine u. Normally we don't do that, but let's see what happens. The numerator becomes 1 minus cosine u squared, and the denominator, after you actually expand it out and cross out the parts that cancel, you get 1 minus cosine squared u. Well, when you take a square root of a fraction, you take the square root of the top and the bottom. So we'll keep the plus or minus for right now. So square root of the top, I think I can see what's going to happen there, and square root of the bottom. However, before I write the bottom, there's something I'm going to point out. There's another way that we can write 1 minus cosine squared u. Do you know what other way we can write it? I'll remind you of something that we wrote earlier. We're thinking 1 minus cosine squared. Earlier today, we wrote this. 1 minus sine squared x is cosine squared x. So now, 1 minus cosine squared u, it's cosine squared u. Wait, did I write cosine? I'm sorry, I didn't mean to write cosine. Here, let me fix what I wrote there. 1 minus cosine squared of something equals sine squared of something. I meant to write sine squared. Let's fix it. So we're using an identity we wrote earlier. That's better. See if I could fit this all on the screen. No, not really, but we had a 1 minus cosine squared of something. Here's a 1 minus cosine squared of something. The identity says it equals sine squared of that thing. So here it is as sine squared of that thing. Now we can simplify a lot because we have the square root of something squared and the square root of something squared. So this equals, here, let's write this with the original left-hand side as well. So tangent of u over 2 equals, I'm going to get rid of the square root symbols and the squaring. Square root of something squared, we just get 1 minus cosine u up top, and we get sine u on the bottom. And I'll put a box around this, and this is the formula, the half-angle formula for tangent that shows up on the reference sheet. Now, the only thing left is I want to talk a little bit about why did I drop the plus or minus sign. At the very end there, I dropped plus or minus. The reason for that is because, first of all, I'm claiming that this is always the plus. Like out of the plus or the minus, this is always the plus. But why is that? Okay. The numerator is something squared, and then you take the square root of it. That's always going to be greater than or equal to 0. So what I'm saying is, when you do 1 minus cosine of u, look at 1 minus cosine of u. What's the largest that cosine could possibly be? Cosine of something can be possibly up to as large as 1. So the thing that we're squaring here is 0 or above, and you take something that's 0 or above, you square it, you take square root. It's going to, the numerator is always greater than or equal to 0 in this case. The denominator, the reason why I dropped the plus or minus is because it turns out that the denominator is always the same sign, S-I-G-N, as tangent of u over 2. Okay, so that's kind of interesting, but the sign of this expression in the denominator is always the same as the sign of this expression here. So we don't need to write plus or minus. All right, so that was formulas for reducing powers. So what's left of this lesson is we want to do a couple more example problems, and we also want to derive one more group from that reference sheet, the product to sum and sum to product identities. Let's derive those first, and then we'll do some examples, okay? So product to sum formulas. We'll do all the deriving first, and then we can just have some examples at the end. Notice, let's go back to the addition formula. This is actually cool. I like the way that we do this. Here's an addition formula for sine. And I'm going to write the subtraction formula for sine. Now, these can be written with u's and v's, or they can be written with x's and y's. They're just labels. Either way is fine. So on the reference sheet, they're written with x's and y's, but I think in the lesson last time we used u's and v's. Or maybe, actually, now that I think about it, we might have used t and s. So, yeah, just a relabeling. It's fine. All right, so the thing that I think is kind of a cool trick, we're going to start with these and try to derive a new trig identity. We're going to add these formulas. Cool idea. Take two trig identities, add them together and see what happens, because they have some similar looking terms. And when I say add formulas, I mean left-hand side plus left-hand side. And then I mean right-hand side plus right-hand side. So the left-hand side plus left-hand side equals. What happens when you add the right-hand sides? There's going to be some stuff that cancels, right? The cosine u sine v and the minus cosine u sine v, they just They just cancel each other. So what you're left with is sine u cosine v plus sine u cosine v, also known as 2 sine u cosine v. This looks like we just found a new identity. I mean, it's kind of interesting, maybe. What we do is we rearrange it. When I say rearrange, I mean algebra. I mean subtracting something from both sides, or dividing something from both sides. So what we're going to do is say, let's write it this way. See what I did there? And this is one of the product to sum formulas. Came from adding two of the addition and subtraction formulas together and then rearranging. So this is called a product to sum formula because the left-hand side is a product of trig functions and the right-hand side is a sum of trig functions. So product to sum. And all I'll say about the other ones is that you could use a similar strategy to derive the other three. So we don't have to do all of them. I'm talking about on the reference sheet, on the product to sum formulas, there are 4 of them. And they all come from combining addition or subtraction formulas. Okay, that's cool. Sum to product formulas. Let's talk about those. Because after we do those, we'll have everything on the sheet either derived or at least discussed. And we'll be convinced that everything on the formula sheet is true. So for this, you know, with a lot of identities, you start with some identity and then you do something to it. What we're actually going to do is start with the thing that I just wrote above. And you see, one of the things about math is we try to derive things in a specific order. There's a certain structure to this. Like, first we had to know the addition and subtraction formulas from the previous video. That helped us get this formula. And now this formula is going to help us get something else. And, you know, there's a logical order here. We're not just doing these in a random order. Okay. A little trick that we do here is we're going to let u equal x plus y over 2. And we're going to let v equal x minus y over 2. Now, this is a kind of substitution that we're making. And, you know, this is pre-calculus, but I'll tell you that in calculus, we also make substitutions like this quite often, where you have something in terms of one letter, and you want to sort of get it in terms of some other letter for something that's going to help you. Well, am I allowed to do it in this way, though? What I'm really doing here, when I say let u equal something and let v equal something, you might look at it and say, like, wait a second, I thought u and v were supposed to be any angles. Now you're telling me they have to be this and this? The reason why it's okay to say that they are this and this is because technically we're not really changing u and v. Technically what we're doing with this sentence is we are introducing x and y to be defined relative to u and v in this particular way. I don't know if that nuance seems important to you or not, but yeah, we're introducing x and y in this particular way because we're going to use x and y for something. All right, let me start a new page. We could almost prove them at the bottom of that page, but let's just start a new one to have plenty of space. Okay, then I'm going to rewrite what I have above, but I'm going to replace u with x plus y over 2. I'm going to replace v with x minus y over 2. That's my new left-hand side. What does my right-hand side become? Check this out. What is u plus v? Here, I'll write sine. We're definitely doing sine of something. What is u plus v? X plus y over 2 plus x minus y over 2. Do you want to do some scratch work on the side? Should we maybe? Okay, u plus v equals x plus y over 2 plus x minus y over 2. Common denominator is 2. So we have x plus y plus x minus y. Oh, look at this. The y's cancel. What is this? 2x over 2. This is just x. Huh, that's pretty cool. That simplified a lot. It's almost like we planned it this way. We set up u to equal x plus y over 2, and we set up v to equal x minus y over 2. We set them up for this convenient thing that was going to happen, because now the right-hand side is going to be x, sine x. And then you could figure out what is u minus v. Similar scratch work, right? Instead of u plus v, do u minus v. Would you believe that this winds up being sine of y? Do the scratch work if you want of u minus v. You'll see it simplifies to y. Look what we just got here. That's pretty cool. We're going to take what we just got and rearrange it slightly. We're going to basically just multiply both sides by 2, and we're going to say that sine x plus sine y equals 2 sine x plus y over 2 cosine x minus y over 2. And this is one of the sum to product formulas. So you see that on the list of sum to product identities. And I'll just say that a similar strategy can be used to derive the other 3, because there were 4 formulas under the sum to product identities. So this is called sum to product because on the left-hand side we have a sum of 2 trig functions, and on the right-hand side we have a product of 2 trig functions. There's other stuff going on too, but just broadly speaking, the left-hand side is a sum, there's the plus sign. The right-hand side is a product, there's the multiplying. Now the rest of this section is going to be example problems where we apply some of these formulas that we haven't applied yet. Before we do the example problems, I want to take just a quick look at this reference sheet. Okay, I'm going to zoom in on it too. All right, fundamental identities. We had talked about some of those a while back earlier in the semester when we had the unit circle and we, first introduced sine, cosine, and tangent. We saw a couple of these then, but we also revisited them in our trig identity lesson 2 videos ago. So we understand why these are true. Let's skip the cofunction and reduction identities for a moment and look at the addition and subtraction formulas. The previous video was all about the addition and subtraction formulas. We derived some of them, not all of them, but we derived some of them. Similar strategy, can do the other ones. And we saw some problems using the addition and subtraction formulas. We were able to evaluate trig functions of angles that we typically couldn't do, like sine of 15 degrees. We couldn't really do that before, but now we could say sine of 15 degrees, you could think of it as 45 minus 30. 45 and 30 are common angles that we know how to work with. So these were useful to us in a problem-solving sense. Another way that these are useful is that you could use these formulas to prove the cofunction and reduction identities. So that's where these come from. Moving down the list, double angle formulas are what we started the video with today. And how did we start? How did we get these? We started with the addition formulas. I think we started with this one, the addition formula for cosine. We started with that, and it helped us get this, this, and this. All right, and similar strategy gets you the other two. Moving up here, formulas for reducing powers. We said that those were just rearranged versions of the double angle formulas. We got them pretty quickly. Half angle formulas. I said that there was a 3-step process to derive the half angle formulas, and maybe that's true for sine and cosine. It seemed like there was a little bit more work involved for tangent, just for the simplifying portion of it, but we saw why these are true. And then we just talked about the product to sum and sum to product. We derived one of each. I guess we derived, the first, because this is really 4 of one type and 4 of the other type, and we did the first of each. Only other thing on the list is the law of sines and cosines. That was a different section we talked about earlier, a while back. And those, I said, are kind of considered separate from the rest of this list anyway. So we've done it. We've basically convinced ourselves that everything on this sheet is true for a reason. A lot of them come from the addition and subtraction formulas. And that's why we had to have a whole video about them. And deriving the addition and subtraction formulas was a little bit weird. We had to use the unit circle. But then the ones we derived today, mostly I think the ones we derived today were a little bit more straightforward. They didn't rely on any kind of weird pictures or any weird arguments using the unit circle. All right, let's do some example problems. First problem I've got for us, it's going to say write sine 5x plus sine 3x as a product of trig functions. Why don't you try this one? Why don't you try this? See what you can do. Pause the video if you need to. All right, what's given to us is definitely a sum of, trig function plus trig function. We just wrote a formula above for sine of an angle plus sine of an angle equals, this is a product of 2 trig functions. So that's the formula we're going to use. We're going to say that this equals 2 sine, what's my x and what's my y? I'm going to underline them. This is basically my x and this is basically my y. Right? 5x and 3x are the 2 angles we're doing. So put those in for x and y. So we're going to get sine of 5x plus 3x over 2 cosine of 5x minus 3x over 2. Technically, we did answer the question. We rewrote this as a product of 2 trig functions, but we should try to simplify, of course. What's 5x plus 3x? That's 8x. 8x divided by 2 is 4x. See, that's a lot simpler. 8x over 2. Just simplify it. 4x. What do we have here? 5x minus 3x. That is 2x, and it's over 2. 2x over 2 is x. So that's a good answer. And this was an example of using a sum to product formula. That's one type of question you could see that uses that type of identity. Next problem I'm going to do for us, I think. Example. I'm not telling you which identity all of these use right away. This one says, if cosine of x equals negative 2/3, find cosine of 2x. Okay, I'll talk us through this one. I guess one thing that comes to mind is if cosine of x is negative 2/3, do I know what x is? Do I know what x is? Like, if this was, instead of 2/3, if this was like 1/2, then I think maybe I could try to figure out what x is, because I know cosine of a certain angle equals 1/2. But do I know an angle that when I take cosine of it, I get 2/3, negative 2/3? Not really. I'm trying to think of inverse cosine, but 2/3 is not really a nice number that we see very often. So let's forget about that idea. Let's try to do this using one of the identities from today. We want to find cosine of 2x, and we have an identity from earlier today that says cosine of 2x equals, there's actually three different right-hand sides, right? I'm looking at the reference sheet and I'm looking at the double angle formulas. Cosine of 2x equals three different things. Of those three things, which one do you think is going to be the most helpful? I think it's going to be the one that involves cosine. So this is the identity that I want to use. Because this has cosine squared x, and we know what cosine squared is. Cosine squared was given in the problem to be negative 2/3. So look at that. Whatever number this winds up being, whatever number this equals, that's going to be the answer. So negative 2/3 squared is 4/9. We can do the rest of this in our head, right? 2 times 4/9 is 8/9. 8/9 minus 1 is negative 1/9. So we used, in fact, I'll write this. This was an example of using a double angle formula. It's one type of problem you could see that uses a double angle formula. The fact that this asked for cosine of 2x, that's basically what clued me in, that a double angle formula would help. Okay, ready for another problem? This next one, I think I will start, and then I'll ask you to try to finish it. So this problem says find the exact value. Of course, this means by hand without a calculator. Of sine of 22.5 degrees. So I'm going to start this one. Let me move the old page away. It's getting in the way. How about this? I said I was going to start this and then have you finish it. I think instead, I'm just going to do this one entirely and then give you a different one to do yourself. Unless you really want, you can always pause this video and try it. But my plan is I'm going to do this one and then give you another one. All right, what can we do? What can we do with this? This is a weird angle, 22.5 degrees. What can we do with that? All right. Notice 22.5 degrees. What do you notice about that? It's not just a completely random angle. There is actually a reason why this angle was given to us. It's because it's half of 45 degrees. So sine of 22.5 degrees is sine of 45 degrees over 2. All right, let's section that off. That was kind of our little brainstorming session. That gives me an idea of what we're going to do with this problem is we're going to treat it as sine of 45 degrees over 2. And then I say, hey, we have some formulas. We have some trig identities for sine of u over 2. Don't we? Yeah. So let's use, let's write it. We're gonna use it. Let's just write it off to the side for right now. There's a trig identity that says sine of u over 2 equals plus or minus 1 minus cosine u. All right, that's what we're going to use. 45 degrees is u for this problem. So somehow this equals plus or minus. I'll write plus or minus, but we know that by the end of the problem, we have to figure out, is it plus or is it minus? 1 minus cosine of u over 2. Of course, don't stop there. We haven't found, like it says find the exact value, so we haven't actually found it. We need to evaluate. But the good thing is we know what cosine of 45 degrees is. Okay, we're going to do a couple of things in this step. First of all, let's deal with the plus or minus sign. Is it plus or is it minus? Now, 22.5 degrees is not one of the nice angles that we're used to dealing with. We're used to things like 30 and 45 and 60 and 90. 22.5. I mean, can you estimate in your head like a little bit less than 30 degrees? Maybe say that. Does that look like maybe 22.5 degrees? I tried to make it look like a little bit less than 30. The important thing is I can tell that it's pointing towards quadrant 1. That's the reason why I was thinking about this. It's a small angle. It's acute. From standard position, it points into quadrant 1. In quadrant 1, sine is positive. Sine is positive. So I'm going to drop the plus or minus symbol and just say it's just positive. Okay, so you do that based on what's the angle that you're taking sine of. And I look at this and I say sine of 22.5 degrees has to be a positive number. My answer has to be positive because of this picture. Okay. 1 minus, what's cosine of 45 degrees? We know that. Square root of 2 over 2. Okay, now I could actually say we have found the exact value, but we can probably try to fix this up a little bit. I don't like leaving a fraction inside a fraction. There's a couple of different ways you could probably do this arithmetic. I'm thinking, I don't know, how do you want to do it? We could multiply this fraction by 2 over 2. Right, like times 2 over 2. That's one way. That's pretty good. We'll do that. It got rid of the fraction, right? But on the bottom, we now have a 4 instead of a 2. Is that a problem, though? I think that's actually a nice thing that we turn that into a 4, because I know the square root of 4. So when you do the square root of a fraction, you do the square root of what's up top and the square root of what's on the bottom. And I know the square root of 4 is 2. So one way you could write this answer is 1/2 square root 2 minus square root of 2. And that is the exact value of sine of 22.5 degrees. There might be other ways that you could write that answer also, but this is the way we found it. And I will label this as, this was an example of using a half angle formula. And I like this problem because, you know, in the previous section, I liked that we were able to evaluate things like sine or cosine or tangent of 15 degrees, which were like angles that we couldn't deal with before. And now we're able to add like 22.5 degrees or maybe some other things like that to the list of angles that we know how to deal with. All right, I said I was going to have one for you to try. Let's see, what kind of problem do I want to give you here? I have a pretty good idea what I want to give you, but let's see. All right. I'm going to ask you to find the exact value of cosine of pi over 8. So why don't you pause the video, take a few minutes, and try to do this. All right, so should we write something off to the side? Is there something we notice about pi over 8? Yeah, I think so. Notice pi over 8 is half of pi over 4. And pi over 4 is one of the common angles that we know how to work with. So cosine of pi over 8 is cosine of, you could say, pi over 4 over 2. The identities that we've been saying in this section work whether the problem is in degrees or radians. Either way is fine. So we could do this. We could use half angle formula on this. Or convert to degrees and say pi over 8 is the same as 15 degrees. Oh, no, not 15. 22.5. I had 15 degrees on my mind because of what we were talking about a minute ago. Yeah, 22.5. Which is half of 45 degrees. Either way, whether you think of it in terms of radians or whether you think of it in terms of degrees, it's going to be a half angle formula problem. So let's write cosine of pi over 8 is cosine of pi over 4 over 2. I'll just leave it in radians. You don't have to convert to degrees if you don't want to. So what does the formula say? There's a plus or minus sign and a square root symbol. Let's just deal with the plus or minus right now. Cosine of pi over 8 is positive. I know that because think about what quadrant it's pointing in. This is a small acute angle. Maybe converting to degrees is helpful here, but I know what a 22.5 degree angle looks like roughly. It's pointing in quadrant 1. This is a little smaller than pi over 4. And yeah, it's pointing in quadrant 1. So cosine is positive in quadrant 1. That's what we get. Now we want to try to evaluate this. I get the square root of 1 plus root of 2 over 2. Hey, this looks similar to the previous problem we just did, right? Yeah, it is similar because one of them was sine, one of them was cosine. And if you think about it, it's really the same angle in both problems. One of them was given in radians and one of them was given in degrees, but same angle, so it's going to be similar looking. All right, this equals, well, we could do the same trick we did last time. Multiply by 2 over 2. And that turns this into 2 plus root of 2 over 2. I'm sorry, 4. So multiplied by 2. Square root of 2 minus square plus square root of 2 over... All right, how does that look so far? One more step and I say we're done. Let's make this 1/2 square root 2 plus square root of 2. And that's my answer. I want to move the page up and show you that it looks almost like the answer we got in the previous problem, except there's a plus sign instead of a minus sign. And it's because we were doing cosine instead of sine that we wound up with very similar answers. All right, let's get a fresh sheet of paper, and I want to say a couple of things about this example we just did. And really the past two examples that we just did. So before I move the page away, I'll say we did sine of 22.5 degrees, and we did cosine of pi over 8. And I'm telling you that, you know, convert from degrees to radians. These were the same angle, exactly the same angle, just one of them was sine and one of them was cosine. So that shows you that these identities work, whether you think of it in radians or degrees. Now, I said something today, a few minutes ago maybe, about in the previous lesson, previous video, we found cosine of 15 degrees. And we did that by using a subtraction formula. Of course, what we just did a few minutes ago, 22.5 degrees, we used a half angle formula. But in the previous video, we did cosine of 15 degrees using a subtraction formula. The subtraction formula that we used was because we thought cosine 15 degrees could be rewritten as a subtraction of two common angles that we know how to deal with. So we said 15 degrees, well, that's just 45 minus 30. Another option is that you could have done this as like 60 minus 45. Just try to find two angles that when you add or subtract them, you get 15. Well, now I'm here to tell you that there is another option for problems like cosine of 15 degrees, is you could use the half angle formula. And I'll show you what I mean, but I'm going to underline. We used a subtraction formula, and I'm saying that you could also use a half angle formula. So cosine of 15 degrees, you could say, hey, 15 degrees is exactly half of 30. So you see, you have options when you're doing some of these problems. And I'll just say this, you know, of course, this gets the same answer. The answer might look different at first, but they simplify to the same equivalent answer. However, for angles such as 22.5 degrees, we must use half angle. Do you see why? See why we have to use half angle? It's that 0.5, isn't it? And it's an angle that I don't think that we could find an addition or a subtraction of two common angles that we know, like 45 minus 30 or 60 minus 45, or even like try to get 90 involved somehow, I don't think that we're going to find two that when you add them together or subtract them, you get 22.5. So addition and subtraction formula is not really an option for this problem. That's why the half angle formula is really nice, because it lets us solve that type of problem. And, you know, or in radians, pi over 8. So if you get something like pi over 8, what's tangent of pi over 8? You know, you can do it using a half angle formula. So we're almost done with this section. That was just some notes that I wanted to say about this. I like that we're able to do sine, cosine, and tangent of so many different angles now by hand, both in radians and degrees. There's still some that we can't, right? Like, what is sine of 17 degrees? That's kind of weird to try to do that by hand. Can we get 17 as like a combination of other angles we know? Feels like that would be really tough. So maybe with some repeated use of like a subtraction formula and a half angle formula, and maybe have to use them twice or something, but I don't think you'll see something like sine of 17 degrees. I was just saying that as an example. All right, one more example. One more problem that we do know how to do for this lesson. Let's express cosine 7x sine 9x as a sum of trig functions. I'd like you to try this, so you can pause the video and give this a try. Okay, so it's asking for a sum of trig functions. What's given to us is a product, right? Cosine something times sine of something. So we need a product to sum formula. So let's use, what product to sum formula do you think is going to help? Well, we could look at our sheet and say product to sum identities. Left-hand side is a product. So which one has cosine and sine? This one, second one. Cosine something, sine something equals this. So that's what we'll do. Cosine u, sine v equals 1/2 sine u plus v minus sine u minus v. Okay. There's a minus sign in here. We have to be careful because the problem told us to express this as a sum of trig functions, and I'm worried that we're going to get a minus, and it's not really going to be a sum. It's going to be a difference. Anyway, let's just get started and see what happens. So cosine 7x sine 9x. So you kind of see what u and v are supposed to be. So this is equal to 1/2 sine of 7x plus 9x is 16x minus sine of 7x minus 9x is minus 2x. All right, are we done? No, we're not done because we have not written it as a sum. Sum means plus sign. This has minus signs. So what can we do about this? If we were in class, I would ask if anyone has ideas, but I'll have to just show you. Look at this thing here under the fundamental identities. Sine of negative x equals negative sine of x. That's what we're going to use, because we would like to rewrite this. Sine of negative something. It says you can pull the minus sign out. and then on the inside you don't have the minus sign. So this is going to be 1/2 sine 16x. When you pull the minus sign out, it gets multiplied by the minus that's already there, so you get plus sine 2x. Oh, that was pretty cool, right? Look at that. Using a fundamental identity to flip the minus to a plus. Did we write it as a sum of trig functions? Yeah, we did. We did. I actually decided to pull the 1/2 out, or I guess you could say I decided to distribute the 1/2. And that's my answer. And it has a plus sign, so it is a sum. And this was our example of using a product to sum formula. So I put this in to make sure that we have now seen examples of all of the different types of identities that we discussed today. We've seen them all show up in example problems, I think. So we've seen a variety of trig identities in this section and a variety of different types of problems. I think if you look through all the actual problems that we solved in this section, they're all pretty different from each other. Express this product as a sum, express this sum as a product, evaluate sine of 22.5 degrees. We also had that one in the middle of the section that was if cosine of x equals negative 2/3, find cosine of 2x. Kind of seems like a unique problem, right? So you might see problems that don't feel like they necessarily fit into a template, and it's up to you to figure out, is there a trig identity that I can use? Is there some way that I can rewrite this angle as a, sum or difference, or maybe this angle is half of some other angle? Anyway, you have to be a little bit flexible and a little bit creative to solve some of these. The good news is that we basically went through that whole reference sheet and derived essentially every type of trig identity that we need. Of course, there are more trig identities that exist. We've seen that we can invent new ones just by merging trig identities together. So we could go on forever doing that. But that's not what this course is going to be about. We are now done with introducing new trig identities. And the next upcoming lessons are going to use them to help us solve some problems. But we're not going to be adding any more to the list. So that's the good news. All right, so the next lesson will be a little bit of a change of pace, but it's still going to be trig. So I'll see you next time for that. Take care.